Chemistry may be the first of your science classes to stress what are called significant figures when performing calculations. Significant figures, or sig figs as we will call them, are digits that are known to be precise. The most common question, or maybe it's a complaint, that science teachers get concerning sig figs is, what's the big deal? Why are these important? Well, scientists collect quantitative data with some type of instrument or measuring device. These measuring devices have a certain degree of precision. When taking a measurement and recording data, scientists are limited by the precision of the instrument. Take these two rulers, for example. The first ruler has markings for every meter. We can definitely determine the length of the room to the nearest meter, but then we can also estimate to the tenths place. A correct measurement with this device would be 11.2 meters, which is 3 significant figures. A length of 11 meters would have too few sig figs, while a length of 11.25 would have too many sig figs. A good scientist needs to record precise data. If you want more precise data, you must use better instruments. Here, the second ruler has the markings every tenth of a meter, so we can definitely read this ruler to the tenths place. Then we can estimate to the hundredths place. The length of the room using this ruler would be 11.12 meters, which is 4 sig figs. We don't use rulers very often in chemistry class. The majority of the time we'll be using glassware such as beakers and graduated cylinders. To determine how precisely you can read the glassware, look for the smallest increments of 10 on the glassware. Our small 50 and 100 milliliter beakers have markings every 10 milliliters. You can definitely read these beakers to the tens place, and then you can estimate the volume to the ones place. For the large beakers we will use, the smallest increments of 10 is the hundreds place. You may notice markings every 25 or 50 milliliters, like on the beaker shown here. But you must have a consistent increment of 10 to read the glassware precisely. These beakers should be read to the tens place. An easy thing to remember when using beakers is that the volume readings will never have decimals. Graduated cylinders are more precise than beakers, which can be seen by how many markings or graduations are on the glassware. 10 milliliter graduated cylinders have markings every tenth of a milliliter. This means a 10 milliliter graduate can be read to the hundredths place. We also have 25 and 100 milliliter graduated cylinders. For both of these types of glassware, the smallest increment of 10 is the ones place. Therefore, a 25 and 100 milliliter graduated cylinder can be read to the tenths place. Volume readings will always have decimal places when using graduated cylinders. Now we have to discuss the rules of determining the amount of sig figs in a number. The rules are best understood by looking at examples. Rule 1 is that any integer that is not 0 is significant. For example, 24 would have 2 sig figs. Both 2 and 4 count as sig figs because they are not 0. How many sig figs does 127.34 have? Take a second. This should not be hard. All the integers count because there are no zeros. Therefore, the number has 5 significant figures. Students don't usually have issues with rule number 1. Rule number 2 regarding zeros is where students struggle. Sometimes zeros count, sometimes they don't. When considering sig figs, there are 3 types of zeros. Let's explain these types and then look at some examples. Leading zeros are zeros in front of non-zero digits. Leading zeros never count as significant figures. Captive zeros are found between non-zero digits, and they always count as sig figs. Trailing zeros are zeros at the end of a number. Trailing zeros are only significant if the value contains a decimal point. Let's determine the number of sig figs for a few examples including zeros. For A, we know that all non-zero integers count as sig figs. So 6, 2, and 1 count. But what about the 0? This 0 is a captive 0 because it is between 2 and 1, 2 non-zero digits. Captive zeros always count as sig figs, so this number has 4 significant figures. Examples B and C are similar to A. Pause the video and try these on your own. Both examples contain only captive zeros, so all the zeros count. B has 3 sig figs and C has 6 sig figs. Example D has 2 non-zero digits that count as sig figs. But what type of zeros are we dealing with? The zeros are at the end of the number, so they are trailing zeros. Remember, trailing zeros only count if the number has a decimal. So in this case, the trailing zeros count because the value has a decimal point. This number has 4 sig figs. Think about E really quick. This number has 2 non-zero digits and only trailing zeros. Do these zeros count? Yes, they do, because the number has a decimal point. Therefore, this value has 5 significant figures. F has 2 significant non-zero digits and 2 different types of zeros. This is a leading zero, and this is a trailing zero. Leading zeros never count. This trailing zero counts because the number has a decimal point. This means the value has 3 sig figs. Take the time to pause the video and try the remaining examples on your own. Seriously, pause the video and try G through J on your own. Okay, let's go through these quickly. For G, these leading zeros do not count. The 4 and 7 count, and this trailing zero counts because the value has a decimal point. 3 sig figs. H has 2 leading zeros that never count. The 3 counts. This zero is a captive zero, so it counts. The 2 counts. This trailing zero counts because the number has a decimal point. 4 significant figures. Example I has 2 sig figs, while example J has 4 sig figs. Do you see the difference? For I, the trailing zeros do not count because the number doesn't have a decimal point. You may have never seen a value written as 1300 decimal point before, but it is completely legitimate. Because the number has a decimal point, these trailing zeros count. One small clarification before we move on. Let's say 0.03020 from example H is a volume in liters that we need to convert to milliliters. We already determined that the value has 4 sig figs. When you convert the value, it must still have 4 sig figs. Students often mistakenly write the new volume as 30.2 milliliters, which only has 3 sig figs. Do not drop trailing zeros when you convert. The actual volume is 30.20 milliliters. The final significant figure rule is that exact numbers have an infinite amount of sig figs. In other words, do not consider exact numbers when determining the sig figs after a calculation. What is an exact number, you may ask? Any constant or conversion factor that may be involved in a calculation has an infinite amount of sig figs. Counting numbers are also exact numbers. If you count 5 bananas in a bunch of bananas, that value has an infinite amount of significant figures, like 5.0000000. You should get the point there. When dealing with very large or very small numbers, you need to make use of scientific notation. I'm going to use a bad example involving counting numbers, but you should be able to apply it to a laboratory situation. The TV play-by-play guy for every Husker game will announce an estimated attendance. Let's say he estimates 78,000 people. This value has 2 significant figures. The trailing zeros do not count. When expressing this value in scientific notation, the number can only have 2 sig figs. So you would write 7.8 times 10 to the 4th. Now let's say the ticket takers get an actual ticket count. They count up all the tickets and they get 78,000 tickets on the dot. This value would have 5 significant figures. So when writing the number in scientific notation, you would write 7.8000 times 10 to the fourth. Alright, once again, it is time to pause the video and practice. Identify the number of significant figures in the following values. Pause the video and try them on your own. The only way to get better is to practice. When you are ready, push play to check your work.